Okay, in this set of notes, I'm going to be talking about one specific type of discrete probability distribution, the binomial distribution. Now, again, this is just one type of discrete distribution, and before we talk about calculating binomial probabilities or do anything specific, the most important sort of first step in dealing with these types of problems is to identify an experiment or a situation as being binomial. So a process or an experiment is said to be binomial if it meets all of these outcomes. So for binomial probabilities, or for a process to be considered binomial, there must be a fixed number of independent trials. So we need a fixed number. Basically, criteria number one is fixed number of trials. Two, those trials are independent. Three, and this is why it's called binomial, outcomes are classified into two categories. Now, we normally call these success and failure. Success doesn't always mean something good. It just means the outcome that we're looking to specify as a probability, and for the probability of success remains the same. So each of the independent trials has the same probability of success. So if all four of these criteria are met, then we say the process is binomial, or the experiment is binomial. Notation-wise, we're going to use lowercase p for the probability of one single success, and that's the probability of one success, and lowercase q, the probability of one failure. N is basically the sample size, or the number of trials. X is going to be the number of successes that we're looking for. So for example, if you're looking for the probability of 4 successes out of 10 trials, then X would be 4 and N would be 10. And again, P of X is the notation we're always using for probability. Examples of binomial procedures would be, for example, manufacturing plant labeling items as either defective or acceptable. So again, we have only two possible outcomes, defective and acceptable. A firm bidding for contracts they will either get or will not get. So those, again, two outcomes. Marketing research firm asking the question, will you buy this? And the responses are either yes or no. So yes, no, defective, acceptable, will get, won't get. These are all binomial procedures. A new job applicant either accepts or rejects an offer, and rolling a dice, you either win or you don't win. So again, there could be multiple possible outcomes, but we categorize them all into one of two groups, either success or failure. So for example, before we establish the formal formula for binomial probabilities, consider this experiment. So you're rolling a dice, you're rolling two fair dice, and we have two possible outcomes. We have win and we have lose. Rolling a 6 is a win, and rolling anything that's not a 6 is a lose. Okay, so what's the probability of winning exactly 2 times in 4 rolls? Okay, so we have a fixed number of independent trials, 4 trials, a fixed probability of success. So the probability of rolling a 6 remains unchanged from roll to roll. So we could look at this as an experiment that's repeated 4 times, or an experiment with 4 trials. So now, thinking back to probability, we'll use the multiplication rule, because we have a sequence of 4 events. 4 rolls, 2 of the rolls will be a win, 2 of the rolls will be a lose. Okay, so basically, we have to think about how many different configurations are possible with the winning and losing. Because remember, when we're calculating probabilities, we're using simple outcomes. We have to count the number of simple ways an event could happen. So how many ways can you win 4 times, or how many ways can you win twice out of 4 trials? Now you could think about it as how many ways could you place 2 W's down here? So we have so this is sort of designating the 4 roles. How many ways could we put 2 W's and 2 L's down there? All right, so for example, you could win first and then lose and then lose and then win fourth. So this would be one possible way to win twice. It's not the only way. So if we listed all possible ways of winning twice out of 4 rolls, there are 6 possible ways. You can win in rolls 1 and 2, 1 and 3, 1 and 4. You could win in rolls 2 and 3, 2 and 4, or rolls 3 and 4. So we have 6 different simple outcomes that all correspond to winning twice and losing twice. So I'm going to look at specifically this first one. So what's the probability that this happens? Exactly this. Win-win and then lose-lose. So coming down here, the probability of winning once is 5 out of 36. Because out of the 36 possible rolls, 5 of them will give you a total of 6. So you could roll a 5 and a 1, a 5 and a 1, a 1 and a 5, a 4 and a 2, a 2 and a 4, or a 3 and a 3. So these are the simple ways that you could roll a 6. So 5 of them out of the 36 rolls. So this first W has a probability of 5 over 36. The second W has a probability of 5 over 36. The third roll, which is a loss, would be the complement, 31 out of 36. And then fourth roll would be a loss. Probability is 31 out of 36. So pop this into the calculator, and you get about 8.5%. So that means each of these individual rolls, so this first one has a probability of 0.0858. And the second one also has the same probability, because in each one of these cases you have 2 wins and 2 losses. So if I go to let's look at, I'll use blue here. If I look at the second case, well, the first win would be 5 out of 36. The next loss, well, we would have to change this to 31 out of 36. The next win, we would have to change this to 5 out of 36. So that would be a win. And finally, the last loss. So for the second case here, win-loss, it would still be 2 5 out of 36s and 2 31 out of 36s. So we get the same final result. So each of these 6 simple outcomes has the same probability. Okay, so each one of these guys up here has a probability of 5 over 36 to the second, because there's 2 wins, and 31 out of 36, or 5 out of 36 to the second, and 31 out of 36 to the second, because there's 2 losses. Now, the number of simple outcomes, well, it was a small number, so we just listed them out and got 6, but the number of simple outcomes is 4 combination 2, because we're choosing out of 4 positions, we're choosing 2 of them for the W. So in this case, 4 combination 2 gives us 6. So to generalize that, and up here, this is the number of successes, the second power. This is the number of failures. This would be the second power. And in here, this is the probability of success. That's the P. And over here, this is the probability of failure. That's the Q. So we basically have P to the power of number of successes times Q to the power of number of failures. We could formalize this, generalize it, and we get the binomial probability distribution formula. So this will give you the probability of X successes. So this, again, this notation, P of X, is the probability of X number of successes. So here, the combination, N combination X, so this is N, C, X. So this gives you the number of different orderings that are possible, the number of ways you could order successes and failures. And then we have X number of successes, so we have P to the power of X, and we have Q number of failures, so Q to the power of, well, the complement, N minus X. Okay, so this is the formula for X successes out of N trials in a binomial experiment. So, for example, what's the probability of getting exactly 6 heads in 10 coin flips? Well, we're in the section for binomial probabilities, so you know it's a binomial probability. But in general, for example, if you're taking an exam over multiple different chapters, you have to identify that this is binomial. You're not always going to be told that this is a binomial experiment, calculated probability. So could say, all right, well, what are the criteria? Does this meet the criteria of the binomial procedure? Fixed number of trials. Yep, there's 10 flips, so 10 trials. Trials are independent. Yep, the result of any one flip doesn't affect the next flip or any other flip. Probability of success is constant. Well, if getting ahead is success, then the probability of getting ahead is 0.5 every time. And so we've met all of the criteria for a binomial probability distribution. Fixed number of independent trials, constant probability of success, and let's just go back to here. Just to verify everything, I'll use green. Fixed number of trials, check. There are 10 of them. Trials are independent, check. Fixed probability of success, check. It's 50% each trial, and outcomes are classified into 2 categories. Well, obviously there's only 2 outcomes when flipping a coin, either heads or tails. Okay, so it looks like we've verified that this is a binomial probability distribution. Now, here's the formula. I'm never actually going to calculate the probability using this formula. I'm going to use Excel because Excel has this built in as one of the statistical functions. So what we're looking for here is probability X equals 6. So out of 10 trials, what's the probability? We got 6 successes. On Excel, the function for a binomial distribution, and again, you don't have to memorize this. If you just start typing in the word binomial, as soon as you get in, maybe if you type in equal, you know what, let's do it over here on the Excel file I have open. You don't have to memorize the function for binomial distribution. If you just start typing in the word binomial, as soon as I get 4 letters in, I have a very short list of possibilities. the first one, binomial distribution. Okay, and then Excel's telling me what I need to input: number of successes, number of trials, probability of success, and do I want the cumulative function, yes or no. So I'm going to say 6 successes out of, and so when I'm ready for the next argument, Excel's putting in bold the argument I want. You could actually, if you have a Mac, this might not come up. I'm not sure. There are some differences between Excel on a PC and Excel on a Mac. But on this version, Excel's walking me through the implication of the implementation of the function. So number of successes is 6, number of trials is 10, probability of success is 0.5, and do I want the cumulative function? Cumulative function means everything from the beginning. In this case, everything up from 0. So if I say x equals 6, the cumulative function will interpret that as x equals 0, 1, 2, 3, 4, 5, or 6, and give you all of those probabilities added up. So I do not want the cumulative function. 0 in Excel, 1 means yes, 0 means no. So if you're looking for the probability of x equals one particular value, so in this case, x is just 6, we want 0 or no for the cumulative function. Okay, so about 20.5% is the probability of getting 6 heads out of 10 flips. Okay, and now we could work with quantifiers. So the first example, what's the probability of getting less than 4 heads and in 10 coin flips? And the next problem, what's the probability of rolling at least 3 sevens in 10 rolls of a pair of dice? Now these are both binomial procedures. In the first one, it's either you flip a head or a tail. Second one, you either roll a 7 or not a 7. And both of them reference multiple different outcomes. So, for example, in the first one, there are 11 possible number of heads. So you can roll, or if you're flipping the coin, if you flip all tails, well, that's here. If you flip all heads, well, that's here. Anything in between, x could take on any one of those values. And again, number of sevens, if you don't roll any sevens, you're here. If you roll 10 straight sevens, which is highly unlikely, you're here, or x could take on any value in between. So now, which values correspond to less than 4, and which values correspond to at least 7? So in the first case, less than 4 means 3 or 2 or 1 or 0. And then in the second case, at least 3 corresponds to 3 or more. 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10. So the cumulative function is used when you want to calculate a range of x values using OR, the probability of 0 or 1 or 2 or 3. Now, Excel only works to the left, cumulative from 0. So Excel can calculate this probability directly, but it cannot calculate the at least 7. So to calculate at least 7, you would have to calculate this on Excel. Basically, we're using the complements rule. So calculate the probability of not rolling at least 3 sevens, and then take the complement of that. So in this case, in red, the probability of this happening in red is equal to 1 minus the probability of this happening in green. Okay, and we could do this quickly on Excel. So less than 4 means 0, 1, 2, or 3. So when I'm using the binomial distribution function, number of trials, I'll say 3. Or I'm sorry, number of successes, I'll say 3. Number of trials, I'll say 10. Probability of one success is, in this case, 0.5. And cumulative function, now I'm going to say 1 for true, or yes. Yes, I want to use the cumulative function. So that number 1, this number 1 is telling Excel to calculate all probabilities from 0 up until 3. So the probability of less than 4 heads, or the probability of 0, 1, 2, or 3 heads, would be about 17%. In the case of rolling the dice, we'll use the binomial distribution function again, but we want at least 7, so the complement of at least 3 7s, the complement would be 0, 1, and 2. So I'll do actually 1 minus for complement. 2 successes, 10 trials. The probability of rolling a 7, so we talked about this before, the probability of rolling a 7 is 1/6, 1 out of 6. So let's say you could roll a 7 by rolling a 6 and a 1 and a 6, a 2 and a 5 and a 2, a 3 and a 4, or a 4 and a 3. So we have 6 possible ways to roll a 7 out of 36 trials. So 6 out of 36 reduces to 1/6. And I'm going to use, yes, the cumulative function. So again, you could use the number 1 or the word true. They mean the same thing. So the binomial part will give me the probability x equals 0, 1, and 2. And then I take the complement of that. So at least 3 7s, probability is about 22.5%. Okay, so, and I'm just restating that here. For cumulative function, 0 means no, 1 means yes. And cumulative function does this, gives the sum of all probabilities for x values 0 up through the x value you input. And again, so for example, find the probability of fewer than 4 successes out of 10 trials with a 40% success rate. So fewer than 4 means 0, 1, 2, or 3, which is basically what we just did with the dice. Okay, so actually probability of success, if we're given 40% success rate, this probability of success would actually be for some reason I can't change that. Anyway, this P would be 0.4 for 40%. But this is the exact same calculation we just did with the rolling the dice and with the flipping the coin. Okay, so on Excel, you have these five different quantifiers: equal, less than or equal, less than, greater than or equal, greater than. So make sure you're using binomial function the right way. So if you want one specific x value, you won't use the cumulative function, exactly x. But if you want a range of values, you would apply the cumulative function. So less than or equal to c means everything from 0 up to c. Or strictly less than c, you want everything from 0 up to 1 less than c. Greater than, that means to the right. So in both of these cases, you would use the complement of the cumulative binomial function. Okay, so here's an example. Manufacturing plant produces widgets and ships them in batches of 200. Quality control standards says that select a sample and approve the shipping if there are less than 3 defective widgets. So you get approval if there are no defects or 1 defect or 2 defects. Anything less than 3. So if 95% of widgets produced meet acceptable standards, so that means the probability of 1 success is 95%, what's the probability the next batch will be discarded? Well, how does this happen? What would make a batch be discarded? So when would this happen? Well, that happens when X, or number of defects, is 3 or more. So less than 3, the batch is good. 3 or more, the batch is discarded. So we want the probability that X is 3 or more. So again, this will give us the probability of 0, 1, and 2. So this in red, what I have here, will give me the probability that the batch will be accepted. So if I want the probability that the batch will be rejected or discarded, I need the complement of this. 1 minus the binomial distribution, and we'll do 2 successes out of a sample size of 20, so that's 20 trials. Probability of success is, say, 95%, and cumulative function 1. So, I'm not going to use 95%. What's the probability of 1 reject? Well, if the probability of 1 good widget is 95%, the probability of 1 bad widget would be 5%. So the 0.05 is the probability of 1 success. Well, in this case, success is a defective widget. So the batch is discarded if there are 3 or more defects. So the probability of 1 defect is 5%, and we want the complement of 0, 1, and 2. So it looks like we have about 7.5% of batches are discarded. Okay, next I want to talk about the parameters of a binomial distribution, and this is one of the benefits of the binomial distribution. The parameters are very straightforward and very easy to calculate. So for example, let's consider, again, rolling 2 dice. You win if you roll a 6 and you lose otherwise. So the probability of winning is, like we saw earlier, 5 out of 36. How many wins would you expect if you played 1,000 times? Well, if about 8.6% are winning rolls, well, you would expect about 8.6% of those 1,000 rolls to be winning rolls. That would be your expected value. So because with the binomial distribution we have a fixed probability of success and only 2 possible outcomes, success and failure, the mean of the distribution is the expected value, which in this case would be about 86 wins. So here are the parameters. The mean of the binomial distribution is the expected value, which is n times p, which is what we did here. 86% of 1,000, so we did n, which is 1,000, times p, which is 0.0858. Okay, so mean is n times p, variance is n times p times q. And If that's the variance, standard deviation is the square root of the variance. So mean is NP, standard deviation, square root of NPQ. So one example here, let's say in a body of text with 2,600 characters, how many occurrences of the letter E would you expect? Okay, so in the problem, normally the letter E is used about 12.7% of the time. So this is a binomial procedure or binomial experiment because we have a constant probability of success, 12.7%. Only two outcomes, the letter E and the letter not E. And we have a fixed number of trials. There's 2,600 characters, and we'll assume these characters are independent. You could maybe make an argument that they're not, but let's say they're independent. Most likely they would be independent. It really depends on the actual text. But we have a fixed number of independent trials with two possible outcomes, E or not E, and a fixed probability of success, the 12.7. Okay, so in a body of text with 2,600 characters, how many E's would you expect? Well, the expected value is 12.7% of the total. So our expected value, or the mean, would be N times P. So you would expect about 330 letter E's. Standard deviation, square root of N times P times Q. So here, if our probability of success is 12.7%, probability of failure is the complement of that. So what's the standard deviation? Well, square root N times P times Q, which is about 17. So now, an intercepted and deciphered message is found to have the letter E occurring 290 times. Is this unusual? Well, the average or the expected number of letter E's that you would see would be here. You would expect 330 of them. So now the question is 290, is this unusually low? Well, our criteria for unusual is more than 2 standard deviations away from average. So if we take the average, which is 330, and we subtract 2 standard deviations, well, 2 standard deviations is 34. So 330 minus 34 would be 296. So 296 is exactly 2 standard deviations below average, or 296 would have a z-score of -2. So yes, 290 is even further away from the mean. So if you converted the 290 to a z-score, you would get -2 point something. Maybe around -2.3, close to -2.3. So yes, indeed, the 290 is unusual because it is below this lower bound for usual values. So if our mean is 330, then 2 standard deviations down would be 296. Oops. Say 296, and 2 standard deviations up would be the mean plus 34, so 364. So anything between 296 and 364 would be ordinary or usual values. Anything outside that range would be considered unusual. So 290 is outside that range. 290 would be considered unusual. Okay, that does it for binomial probability distributions and parameters of the binomial probability distribution. Later, when we talk about the continuous normal distribution, we'll look at ways to use the normal distribution to approximate the values of the binomial distribution. But that's a topic that we'll talk about later on. Okay.